Yeah, so welcome everyone, really great to see you. Today we've got Jeff Clark from Energy My Way to talk about everything you want to know about heating your home with heat pumps. So heat pumps are really important because so reducing the carbon impact of home heating is really important because it sort of makes up about 20% of the UK carbon footprint, both sort of hot water and home heating. And of course, most of us, like me, it's definitely have a gas boiler in the house, and that's just emitting carbon the whole time. Heat pumps are a way of helping this because they run on electricity, which allows us to make that a renewable source. And they're more efficient than the electric heaters that we have at the moment, or they can be more efficient if you set them up correctly, which Jeff's going to talk about. So yeah, they have real potential to be very helpful. I'm really pleased that Jeff's taken time to do this. It's now because it's a really, really good time to be learning about heat pumps, because the government currently are giving people money to install them, although there are some issues with the scheme, as we were talking earlier. So that scheme is currently running for about 18 months, and you can get a sort of a few £1,000s from the government if you're a homeowner to support that. So yeah, really good time to be learning about heat pumps, and they're going to be, I mean, all of us probably will be talking about them within the next few years. It's the next big thing, I'm sure. So yeah, really thank you, Jeff, for coming. So just to quickly, the plan for today, Jeff's going to do his talk, and I think I think you're going to maybe stop for some questions as for Clara, to make sure people are to see where people are understanding, sort of whether people are sort of understanding it or not. But we can do a question and answer discussion at the end as well. That's quite good to do. But yeah, otherwise I'm going to let Jeff run his slides. So thank you, Jeff.
Okay, thank you, Nia. Good evening, everybody. I'm going to go through a standard presentation set of slides. A few of them I'm going to skip because they might be a little bit too technical and might get bogged down on them, but they might be relevant if there's any questions, so I can refer back to them. So let me introduce myself. I'm Regional Director for Energy My Way Hertfordshire, which covers Hertfordshire into Essex, North London, and into Bedfordshire and Berkshire. We are local renewable experts, but nationwide. It's a franchise arrangement, and we've got about 8 offices ranging from the north of Scotland down to Oxford, which covers sort of the southwest area, and then Kent, Sussex, and a few other little places in between. Our aim is to reduce carbon emissions of UK property by providing best advice and first-class installations for the complete range of renewable energies. So we deal with solar PV, solar thermal, air source heat pumps, ground source heat pumps, and to a lesser degree biomass. Again, it's one of these things where the government noises that are made have not really supported biomass in the domestic market, and the actual demand has tailed off for more on domestic, and it's still there in the background for commercial. And our mission is to switch UK properties.
Quickly, sorry, Jeff,
yep.
Sorry to interrupt. Were you going to do share in full screen mode?
Oh, apologies. No, I was just looking at my. Hang on just a second. Cancel. There we go. Can you see that? Is that okay?
Yes, that's brilliant.
Great. So our mission is to switch UK properties onto renewable energy and reduce the pressure on the planet and the pocket. Renewable energy should reduce bills, help meet planning constraints, and reduce your carbon footprint. And there are incentives which you can receive return for the government cashback schemes such as the Green Homes Grant and Renewable Heating Incentive. The important one, as far as we're concerned, is reducing the carbon footprint. Overall, that covers a multitude of different areas. It gets you through planning for certain properties, new build or major rebuilds. And also for people who want a more sustainable future, you can do it as a retrofit. And heat pumps come within that element of reducing the carbon footprint. We always say don't necessarily chase the incentives, but use them if they're there. It should be more of a peace of mind to say you want to do the right thing, you want to reduce your carbon footprint, and if the government helps, take it on board. Some people, they follow the incentive and it just doesn't quite sit right with us. Oops, wrong way. And so I start off with new builds. So we give free unbiased personalised advice on most appropriate renewable technologies. It's easier to incorporate renewable technologies in a new build rather than retrofit. It's actually more bespoke and it suits the application. As I say, we can do different technologies, ranging solar, thermal, solar PV through to heat pumps. And we can advise on the subsidies and incentives that are out there. Importantly, we're fully MCS accredited, which means there's a quality of installation service and also an element of consumer protection involved. We think that the way forward with heat pumps is that any installer should be MCS accredited. Think gas safe, think NIC, EIC, anything to do with safety and consumer protection. Hopefully that's the way it will go, and it means then that the quality of installation should be there. And with the new builds, we work alongside the architects and main contractor. So we make sure that our equipment is integrated correctly at the right time. So we take it from drawing stage to project completion. So that's the new build side of things, which is the big market going forward. From 2023, it's just been brought forward from 2025. No new properties are to have fossil fuel heating hot water generators. So it's all going down the route of hopefully going down heat pump, electric. Bear in mind that a lot of the electricity in this country that is generated now through renewable sources, and probably nuclear, if it's done right. Can't see a problem with that. So as I say, these are the different technologies: heat pump, solar PV, biomass, ground source heat pump, solar thermal, and bringing it all together for the whole house. So here we are, heat pumps. What is a heat pump? Think of an amplifier, a multiplier, and what you're looking to do is get a figure and multiply it by a figure to get a bigger end product. So we're looking at, whoops, if you've got a heat pump, you're looking to take 1 unit of electrical energy and try to then use energy from either the ground or the air to try to get your multiplication factor. So 1 unit to 4 units of energy from the ground, therefore you're producing 400% of the energy you need. Heat pump slightly lower, 300 to 360%. So heat pump, think amplifier, multiplier. It basically works with the refrigeration circuit like your domestic fridge or freezer in reverse. So you put a warm can of drink in your fridge, the refrigerator through the refrigeration cycle will take that heat energy out, and then it's thrown out the back of your fridge freezer as heat energy, and that can in theory becomes a lot cooler. So think refrigeration in reverse. You're not cooling, you're heating. It takes low grade heat to a high grade heat, and this is done by the refrigeration circuit and refrigeration process. So I won't go too much on this, but the air source heat pump acts as an evaporator. It basically, the compressor, basically within the refrigerant cycle, it compresses the liquid, it becomes a vapor, creating more heat energy. This is transferred via a heat exchanger into the domestic hot water and heating circuit. As it cools down, it becomes a liquid. It goes through an expansion device, back into a low pressure liquid, and the cycle goes around again. It's quite technical and complicated, but it's what you've got in every refrigerator, your car air conditioning. And this in heating basically works in reverse. The basic components in a heat pump: you've got a compressor, expansion valve, which changes the refrigerant from a high pressure to a low pressure liquid, and a heat exchanger to put the heat energy into your hot water or heating system. And the evaporator coil on the heat pump, the heat exchanger on the rear is on the rear of the heat pump, and it's this box of tricks that is the heat pump. Are there any initial questions or queries on the heat pump? No? Good. How heat pumps save money? It's the efficiency. It's the coefficient of performance. It's a ratio. The coefficient of performance is basically taking the output, i.e. your heat output, and you're dividing it by your input, which is the energy input. So the equation is Q over W. Q is the heat supplied or to be removed from the reservoir. W is the work consumed by the heat pump, the input. So 1 unit of electrical power hopefully becomes 4 kilowatts of heat output. So for 1 unit of electrical, you get 4 kilowatts of heat. So that's where you get the efficiencies. So the COP, the coefficient of performance, is 4 kilowatts divided by 1 kilowatt is 4, which makes the heat pump 400% efficient. If you remember that 400%, when we go on to some tables a little bit further on, you can see the comparison to other heat sources. Gas boilers, oil boilers, LPG, standard electric heaters. So that 400% is what we're aiming to achieve as best as possible. The heat pump works different to a gas boiler. Gas boilers are on, off. There's a boiler, a burner. There's very few that actually modulate in the domestic market. Commercial boilers, they do modulate. They're a lot smoother. They don't just go on, off. Whereas a heat pump tries to maintain the temperature, and there is less switching on and off, so it's more efficient. It doesn't wear the components out, and it ticks over in the background and ramps itself up and down as required. So that's one of the changes in the heating behaviour between a boiler and the heat pump. So a lower flow temperature, but the heating remains constant, more economical, and a more comfortable environment. The heat demand is balanced and adjusted automatically, and it maintains a sensible heat in the building fabric. So that we try to make sure that the building is well enough insulated so it holds the temperature, and we're not blasting raw energy in like you do with a gas or oil boiler in order to put the temperature up as it drops. Weather compensation, I won't go into the ins and outs of it, but heat pumps use weather compensation in most part. It basically monitors the outdoor temperature, and it allows the heat pump to modulate its output in accordance with the outside air temperature against the required flow temperature. This means that if a building's sitting in an area where there's a lot of sunlight and it starts warming the structure up, the heat pump holds off and then it modulates itself, thus becoming more efficient. Is there any queries on that or questions? No? Good. Okay, this is the different types. This is the more generic stuff, and it's not so complicated or technical. So the first type is the ground source heat pump, which is basically takes heat energy from the ground. The second type is an air source heat pump, which takes heat energy from the air. Basically, the air source is a one-off box in most cases, and the ground source is a one-off box, but it's mounted internally in the actual property or in a plant room, and it takes the heat energy via different methods from the ground or from water. So a closed loop system, which is a ground source system, it has the ground loop pipes in the ground, as we can see there. This is a trench idea with a slinky. Again, this is the ground collector. This shows a number of slinkies joined up, and this is a horizontal trench. The horizontal trench, basically up and down, with the slinkies overlap like a flattened spring, which means there's more surface area, and you can use a smaller ground area to get more collection. But it does need to be designed correctly so you're not overtaxing the ground and the ground can recover. Our preference between the two is for horizontal trench collectors, because there's less risk of damaging the environment, the ground. You might even get a permafrost in summer if you're taking too much heat energy out. So we need to be mindful of that. We've got to let the ground recover with solar gain and with water that brings it all back up to speed. Our preferred method over the other two is boreholes. We've just done 2 projects, both of them where we've actually gone down to 120 metres on 2 boreholes on each of the 2 projects. This is because the ground area that we had was limited in size to put horizontal collectors in or even slinkies, and we had enough room to correctly configure the system so we can have 2 boreholes. There's a lot of mess with boreholes. You've got a drilling rig, you've got lots of plant to get onto site, but it is more efficient than the other ground collectors and also air source. So we can drill with our equipment down to 200 metres, and you get the best performance as the ground temperatures are higher than air temperature on average throughout the year. So in winter, the deeper you go, there's less change to the actual temperature. It remains more constant. The most expensive ground loop method could range from 55 to 60 pounds per metre, so it's not cheap. And you're talking about a 90 metre borehole would cost about £5,000, which is just for the pipe work and the filling. That doesn't include for the plant room infrastructure, the heat main that goes to the actual property. Open loop systems are where you take the heat energy from the likes of wells. So you could drill down for 2 wells, and then you can then basically have water going in and out of the wells. Or if you've got a lake, pond or river or creek, you'd have a potentially an open loop operating on that, or you can mix and match with wells. You do need to get permission of the Environment Agency and the local water authorities. You just can't go ahead and do it. If it's on your own land and you've got a lake, you can do it, but you need a substantial amount of water to make that work. So there's another example there of using a lake, and the collectors lay in the lake, and it basically creates a circuit. So it takes heat energy into the heat pump, and then it basically goes back out again, warms up again, comes back in again. Air source heat pumps, as it says, it takes heat energy from the air and it transfers it into water, air to water heat pump. So the idea is that it takes air off the back, it takes the heat energy out, and it discharges cooler air off the front discharge. Most heat pumps nowadays can work quite easily down to -15 degrees. Go back a few years and there was a big fall off in performance when we went down to maybe -5. But there's new refrigerants, a lot more sort of greenhouse gas friendly, shall we say. And they basically take on board heat energy from the air, and that refrigeration circuit takes the heat out that goes into the property, and then, as I say, discharges back into the atmosphere. And this is a general schematic of a monoblock system. We do predominantly monoblock systems. They're a lot more simpler to install. You don't need a refrigeration engineer unless there's a problem. And we do need to put glycol in the water system to stop freezing. So it's a one-off box that basically it has got a flow and return. And then once you get inside the property, we're very much like a traditional heating system, where we have a control valve that will take the heat energy into either a cylinder for hot water or into a radiator underfloor heating system to do the heat. So that's a mono block, a one-off unit, mono, and it just sits there, takes the air in, takes the air out. The other type is a split system. The split system requires a refrigeration engineer to carry out the installation, and a refrigeration circuit is utilized with a hydro box. So the idea is that you've got refrigeration pipework that goes to a box inside, which does the changeover to provide the hot water for your heating and your domestic hot water. The main advantage of the split unit is that you can have the distance of the heat pump from the property a lot further than you would with a monoblock heat pump. You can go, for example, 15 meters is an optimum distance for a monoblock unit, whereas you can go 30 meters, maybe 50 meters with good refrigeration practice with a split system. The installation is a lot more complicated and it's a lot more involved, and there's certain applications that it can be used for, but we wouldn't say that it's going to be more straightforward than putting a monoblock in. It's horses for courses. And just to throw this in the mix, there's also an air-to-air heat pump. This is what you would know as an air conditioning unit, or correctly termed a comfort cooling reverse cycle heat pump. So instead of changing the air that you take from the outside and put it into water, it basically, via refrigeration circuit, uses air, and it can then reverse the cycle to provide either cooling or heating. It doesn't provide domestic hot water, and you can't use it with underfloor heating. It's like a room-based air conditioner. And the main thing to consider is that some companies are selling these as heat pumps, which they are, but they are not a heat pump in the eyes of the RHI. You don't get paid any subsidy on the RHI, the Green Homes Grant. They're considered more of a luxury, but they do provide a very, very good form of heating. So if we look at the comparison between ground source heat pumps and air source heat pumps, generally, as I said, ground source heat pumps are a lot more efficient over the course of the year, especially in winter months. So you would get a seasonal performance factor of 4 from a ground source heat pump versus maybe 3.6 for an air source heat pump. Air source heat pumps are a lot cheaper to install. The actual kit and the kit installation is very similar, but it's the ground collector, the trenches, the boreholes, which put the price up drastically. But you get a more efficient system and a more streamlined system. The ground source heat pump does receive a higher subsidy on the RHI payments, which we'll come on to a bit further on. And the positive for the air source is it's less destructive, the installation. Another one there which I could have put on is that maybe some people don't like to see a box outside their back garden or side access. That's a downside with the air source. You need to consider where you're going to put that outside box. Performance. As we said, a ground source heat pump is more efficient compared to an air source heat pump. The ground temperature doesn't usually fall below 10 degrees C in the winter, whereas if you imagine that external ambient temperatures in the air could be on a regular basis -5, -6. Most heat pumps will accommodate that, but some of them there will be a drop off in performance. You don't get that with a ground source heat pump. An air source heat pump extracts energy from the outside, which will fall below 0. It will work down to -15 quite easily, but there could be a drop off in performance. And due to the heat source, the ground source heat pump will achieve a far better coefficient of performance in the winter and a better overall seasonal coefficient of performance factor. Seasonal coefficient performance is basically looking over a period of time, normally over a period of a year. The coefficient of performance is an instantaneous measurement in the units of power that can be measured at any one point in time. So that's the COP, and the SCOP is over a year. The customer should consider their initial capital costs. Ground source heat pump installations will always be higher, but the RHI does encourage sales. There's a bigger payback from the government in terms of grants. If you're doing a bigger new build project and you can absorb the cost, we would advise a client to maybe look at it on that basis. For retrofit, it's probably not the best thing to do unless you're doing a major refurbishment job. Right, any questions on heat pumps in general? Oh, good. Why choose a heat pump? So this is based on the Energy Saving Trust's advice when you should consider a heat pump. We particularly recommend considering a heat pump if your home is one of the approximately 5 million properties that are off the gas grid, or if you've got a new build property that hasn't got a gas connection nearby. Heat pumps are not recommended to replace existing gas boilers at this time. What we would say is that there's a caveat: unless the gas boiler needs replacing because it's on its last legs, or if it needs upgrading. For example, let's say that you've extended the property and you need more heat output, and there's two things to consider. One is upgrading the boiler, and do you need to upgrade the incoming gas main to serve that boiler? As a generalization, and this is 100% of where it's all coming from, is an ideal replacement for oil or LPG. Oil and LPG, they give us a very high carbon footprint, certain amount of pollutants go in the air. The actual cost of the fuel is quite expensive. You're relying on an outside source for supply. And at the end of the day, if you get a spillage or the lights from an oil storage tank, it makes a hell of a mess, which I've seen on a few instances. Another option which we consider is a logical heat pump replacement is for traditional electric heating. If you imagine that standard electric panel heaters, you've got 1 unit of input energy for 1 unit of output energy, you're getting 4 times as much, 400% more efficient than an electric heater. Going back to new builds, new build developments, 20% of the energy used must come from a renewable source. So installing a heat pump in some of the houses helps meet this target. The easy quick fix, which a lot of people go for, is solar PV. It fits the bill, but we believe that heat pumps are going to provide a much more tangible source of energy. Problem is that some of the planning requirements are showing that the local authorities might say you need to put 1 PV panel on a property. Well, it doesn't do a lot. It just basically ticks a box. So unless there's a bigger number, higher number of PV panels deployed, we believe that a heat pump will give more bang for your bucks in terms of having a renewable technology. Basically, the developer or the self-builder can also review the offset of cost of a heat pump against savings for an upgraded or new gas main and the associated work. So apart from the fact that you've got to put a gas main in, the pipe work and the valves, you need trench work, you need then to backfill, you need to either landscape or put a drive over the top. With an air source heat pump, chances are you don't need to consider any of that. So there's a major saving that is normally not thought of at the initial stages because of the lack of knowledge about heat pumps. So it's a big saving. And also you're not using the fossil fuel, importantly. It's just been brought forward by the government. In 2023, gas boilers will no longer be an option in new builds, nor will oil boilers or LPG. So we're looking to strongly reinforce the deployment of heat pumps, but there's other technologies coming along. We're looking at, there's hydrogen cells, carbon dioxide. So there's all different things in the pipeline. But as far as we're concerned, the main established alternative of heat pumps in the short term is the way forward. And there's still government incentives out there, which are the Renewable Heat Incentive and the Green Homes Grant. Green Homes Grant is for retrofit only. Renewable Heat Incentive is for new builds and retrofit. And it's aimed at the self-builder or the individual. It's not for developers. It's not for building contractors. It's really for self-builders and people who are building their own properties. How does it fit in my property? So this is the outline requirements and a couple of examples. We like to see a well-insulated property, and it's the key to making sure that the heat pump runs efficiently. New builds, the property should already have a decent standard of insulation in accordance with building regulation requirements or better. A lot of clients who are self-builders are taking this on board and now looking to try and increase the insulation levels, which in theory means a tighter building envelope, and it means that a smaller heat pump can be deployed and the running costs are lower and the carbon emissions are lower. The only caveat to that is that if there is a large hot water demand, then we need to factor that in with the heat pump sizing. But as I say, the good thing is that the insulation levels are now being looked at in a lot more detail, and we'd like to see maybe an improvement in the standards, which are already quite good. With retrofitting, it's completely different. You can have different houses, different buildings of different ages with different insulation qualities, ranging from solid walls through to 1950s, 60s, where we're starting to see cavity walls. A lot of these aren't filled. And then as we go through the sort of 90s through into the early 2000s, we're seeing more insulation deployed. So as you look at the buildings, in theory, any property can have a heat pump deployed. However, we'll be concerned about the efficiency of that heat pump in order to make sure that we can accommodate the heat losses in the building practically, and we don't have any silly running costs where people are paying fortunes to run the heat pump. So we always say, as a rule of thumb, for retrofit projects, and this goes back to back with the RHI applications, we like to see a minimum of 300mm loft insulation, or if on the back end of the roof between the trusses, for example, the client could put 100mm Celotex or Kingspan insulation. Where there are cavity walls, they should be filled where practical with a good quality product such as Kingspan. Rockwool will do a more, I don't know, robust filling rather than getting blown particles in that are not potentially the best. And the other one, which is not mandatory for the RHI, but it is something that we always recommend, is ideally all windows and doors should be double glazed, and they should be of a reasonable quality. This basically then gives the homeowner peace of mind that the fabric has been to a certain level whereby the heat losses have been reduced as much as possible to make the heat pump work efficiently. So the idea is that we're looking to try and keep the heat pump running costs down going forward. There are some contractors out there who hedge the bets and put the largest possible heat pump in, which does defeat the object for a load of different reasons, which I won't go into. So the idea is to get it sized as close as possible to get the most efficient running. General considerations. A heat pump is suitable for heating and hot water provision, and it can serve underfloor heating radiators or fan coil units. The water flow temperatures are lower than traditional boilers, be they oil, gas or LPG. And with underfloor heating installations or correctly sized radiators, we like to see a flow temperature of 35 to 45 degrees C, which promotes the heat pump efficiency. If we go back to the seasonal coefficient performance, you saw a figure there, 400%, and you're looking to achieve 1 unit of electrical energy to 4 units of energy from the air. This is the sort of flow temperature that we're going to get those efficiencies. If we're having to run at higher temperatures, because we're putting in, for example, radiators that need to be sized accordingly, this is where we've got consideration given to radiator sizing. It means that the efficiency dropped because we're running at high temperature. So that 400% might be going down to 300, 320%. Still very efficient, but it's less efficient compared to underfloor heating or a well-insulated property. Air source heat pumps and ground source heat pumps are available in single phase electrical configuration from 4 to 16 kilowatt. That's purely down to the electrical characteristics of the actual box and the compressor. And you can't get anything on a one-off box on single phase higher than these sort of figures of 16 kilowatt. So that will be suitable for a property that's well insulated up to 300 meters squared. Ground source heat pumps, they're available with 3-phase units, and we can go up to outputs such as 30 kilowatts. So that's suitable for larger properties, commercial properties. But it's not to say you can't use an air source heat pump for larger properties, because you can couple them up and run them in a cascade fashion. So you basically link heat pumps together, and it becomes a cascade setup where they all run in perfect harmony, and they provide heating with a larger output. And we've done a few of these. We use certain products that are easier to do than others and simpler to run. So the idea is simplicity and keep the efficiency going. Whoops, and excuse me. Heat pumps obviously do the domestic hot water, which is for your bath, showers, kitchen sink. And the general design temperatures we try to work to are 50 to 55 degrees C. You find that most domestic cylinders with gas or LPG, they're sitting there at 60, 65 degrees. So again, it keeps that efficiency going. And there's a little bit more with the cylinder configuration coming up soon. That's just a general schematic. You've got the heat pump external. It basically goes in via a 3-port valve, like your traditional heating system, into a cylinder. Cold water goes in, hot water out. That valve will then switch over, and it will then provide hot water to the heating system. And it basically, the red is the flow, and it all comes back on common return into the heat pump, which then continues through the cycle again. So it's quite straightforward, very similar to your domestic system with gas and LPG and oil. You can couple heat pumps with solar thermal. You would have a cylinder that's got a twin coil configuration. So one would be served by the heat pump, and then one served by a solar thermal system, which means technically you would have very little running in summer of your heat pump. And you could expect something like 75 to 90% savings if we get a good summer against the running cost of your heat pump. And quite a few clients who are doing new builds like to factor that in. And it's also a good, happy marriage with solar PV, because PV generates electricity and electricity runs the heat pump. So again, more potential savings, and combined it reduces the carbon footprint of a property very, very well. So you could factor in calculations for the PV and the heat pump, and you come up with an overall potential carbon footprint reduction. Running costs. This is something where, if we go back to efficiencies, we need to be mindful that the heat pump system needs to be designed and installed correctly. We've seen instances where the running costs that we're just going to touch on as examples have been far exceeded. So it's important to get the design right and the installation right. So an average 120 metre squared house, 2 or 3 bedroom, average electricity use, this could be 4,000 kilowatt hours for standard rate electricity, and gas could be using 20,500 kilowatt hours at an 83.5% efficient boiler, which gives 17,000 kilowatts of heat. So you can see that there's more gas goes in, less energy comes out. It's because it's not 100% efficient. This is based on an existing boiler that could be over 10 years old. If you're looking at newer boilers, you'll be coming into the region of maybe 95, 96% efficient. So older boilers already, due to wear and tear, general design, you put more energy in than what is actually given out. That's quite relevant to comparison with a heat pump. So if you look at actual costs, you could be spending £1,127,000 on heating and hot water, and an electrical amount of, I think it's a bit light, but £520 per year for lighting domestic appliances. When you're looking at putting the heat pump in, you're looking to drastically take gas or oil out of the equation, but you are increasing your electrical consumption a certain degree. So if you see on this chart, the first one is, well, that's gone up to closer to, should we say, £800 to run that heat pump. So you've increased your electrical consumption by potentially about £300. But you need to look along the chart to see the comparison with the other heat sources. So natural gas, this is based on the older efficiency boiler. So if you had a newer boiler that was a bit more efficient, that would be a lot lower in the running costs, and it's probably going to come down to about £1,000. So there's not a lot of great difference, and this is one of the reasons why we say, is it logical to replace a gas boiler with a heat pump? But immediately we start, forget the economy 7, because there's not much of that about anymore. They're trying to do away with those tariffs, economy 7 and economy 10. But you start looking at heating oil, LPG, coal and electricity. You can see the massive potential savings on heating bills by using a heat pump. Oil and LPG are probably more common than coal, and there's still quite a few properties out there that are off-grid using electricity. So the interesting one is that you're still using electricity for panel heaters, but you're using that heat energy from the air or the ground with a heat pump, which then increases efficiency and reduces the running cost. So this is what these figures are based on. And you can see with regards to heat pump, as we said, that we're looking at maybe 300%, 400%, and there's the others, 49%, 39, 61, 39, 32. We haven't got new gas boilers on there, but you're still looking at 95%. So they're still going to be less than 100% efficient. There's a basic monoblock heat pump. This is an older version NIBE heat pump. And what you have with NIBE, that you buy a kit so everything's compatible to suit a heat pump. You get the actual heat pump. We then have a buffer vessel, which I'll explain later, and the hot water cylinder. They're all designed to complement each other. And it's quite important that the right equipment is put into the package. So the estimated installation cost of an air source heat pump, this is based on a 12 kilowatt heat pump, similar to one in the picture. As an estimate, £12,000 to install. The annual running costs, £1,235. This is more than the previous one. This is a larger heat pump than that original example of 120 square metre property. This is probably looking at something 200, 250 square metres. The annual bill saving compared to oil, £1,626. So it's not insignificant. And then you look at the government's incentives and renewable heat incentive payments. You could be getting something in the region of £1,600 a year, which is still pretty much thereabouts. You combine it all together for 7 years of the scheme, the RHI scheme, and you could be saving £22,834, or financial gain, not saving, but financial gain. So if you're doing a change out compared to an older oil boiler, you could achieve that sort of figure. If you're doing it with a gas boiler, you're probably going to find that you're probably going to be getting around about the 11 or 12,000 pound mark. So that's the beauty of looking at oil and LPG alternatives. So that quite clearly over 7 years will pay for that installation. And it will also probably contribute that if you have to do any upgrade work in terms of radiators or pipe work configuration. And the ground source heat pump, that's basically more like, shall we say, white goods, American upright fridge freezer, so it can go in a utility room. So again, you have specific pieces of kit that go together with the heat pump. So on this instance, we got quite a larger output heat pump, 24 kilowatts. This will do quite a large property, maybe something like 400 square meters property, ideal for a new build. You've got a buffer vessel as well, and then you've got, again, a cylinder can be provided to match the heat pump, so it looks quite nice in the utility room, rather than having the traditional circular cylinder, which you can still have with these heat pumps, but this looks a lot nicer if you have it in a utility room rather than the plant room. So with this particular heat pump, the estimated installation costs about £30,000. That will give you a trench type system rather than boreholes. Boreholes are more expensive. That's all the kit installed. The running costs £1,112. Even though it's a larger output compared to the air source, because it's more efficient and it's based over an annual period, because of the temperature of the ground and below ground, and there's less change in temperature, you're going to get more efficiency, so therefore the running costs are lower. Bill savings compared to oil, 1,750, and this is the interesting one. You get a higher rate for the renewable heat incentive, so you get potentially £4,372 per year in this instance. So over 7 years, your combined financial benefit is £42,854. So again, that more than covers the actual cost of the installation. If you do go for boreholes, you're not going to get much change out of that. So you're probably going to come up pushing cost neutral if you went for a borehole installation, which is much more expensive. But again, there's more efficiency to it. So the government incentive is doing the right thing there. It's attempting to get heat pumps deployed and trying to get the cost down, the capital cost down. Domestic hot water. This is something that is very relevant to heat pumps. Historically, hot water has always been stored at 65 degrees or above due to high temperature flow from traditional boilers or LPG and gas or an immersion heater. There's a traditional cylinder, water in the bottom, you've got a coil, you've got an immersion heater, and the water goes out the top. A lot of these have just got a simple jacket on or not insulated, so there's a lot of heat loss, very inefficient. And since heat pumps have a low flow temperature and we try to maintain at 55 degrees, we need to look at two things. One is the pasteurization to do with Legionella. And we have to pasteurize the tank to remove any threat of Legionella because we're sitting at a lower temperature. And if you're out the property for weeks or months at a time, it becomes more of a risk. So periodically, we set up the new heat pump cylinder to increase the temperature to 65 degrees for an hour, maybe once a week or once a week or once a fortnight. And that looks at the killing or reduction of growth of Legionella. So Legionella grows between 20 and 45 degrees C. It's the same in any system, not just a heat pump system. So if you're running your traditional boiler system at a lower temperature, you can still have that problem. If you're not running the water off regularly and it's on tick over, again, you might have this issue. But heat pumps, because of the lower temperature, that's a safety measure that's put into place. The other thing was insulation. This would be something that is second nature to a heat pump installation. Apart from the coil configuration to suit the heat pump, all of the cylinders need to be of a certain standard for insulation levels. We don't want to see heat loss through the cylinder. We don't want to see those plastic fibrous filled insulation jackets. We want to see a proper high quality insulation barrier. And the heat pump system can hold that temperature with maybe 5 to 10 degree drop over 24 hours. So it's quite important in terms of efficiencies, not just for heat pump, for general cylinders. And that's the way it's going. There's a lot more cylinders of this nature on the market over the last, 15, 20 years. We mentioned buffer tanks, and this is something that you wouldn't have on a boiler system. And this is to store hot water for the heating circuit. And it basically stores the hot water to ensure the efficient running of the heat pump. So it maintains the required flow rate through the system. And it also maintains the temperature when the heat pump goes into a defrost cycle. And it allows the heat pump, in most cases, to concentrate on maintaining the required temperature in the buffer than the actual room. So the idea is this is maintained by the heat pump. It's then drawn off with the radiators and underfloor heating, which have got their own control. And again, it aims for efficiency. And these are not very large cylinders in most cases. They're about a quarter of the size of a cylinder, a normal domestic hot water cylinder. Heat pumps are more complex, as you can see with this schematic, compared to a normal boiler system, especially a combi boiler. So you can see why there's a lot more cost to a heat pump system. It's all based around trying to use the heat pump in the most efficient way that we can. Heat emitters. We can use heat pumps with both radiators and underfloor heating. With regards to underfloor heating, they run at lower temperatures. The systems, most manufacturers do not want their pipework to be exposed to over 45 degrees. So it works very well with a heat pump, especially if the buildings are very well insulated. It's more comfortable heat. There's no visible radiators. And in theory, it should be cheaper to heat the room than radiators because it holds the heat more. Normally, you would have a ground floor, which is a solid ground floor with insulation, and then the first and second floors are intermediate floors, and normally timber construction. So you can see on here, we've got radiators upstairs in this instance, and then we've got underfloor heating on the ground floor, which makes for a more simpler installation. However, you can use underfloor heating on the upper floors. I'll show you something in a second on that. So going back to efficiencies with new builds, you'd have a structural slab, and then it's mandatory to have an insulation layer that meets a certain U value, i.e. To look at what heat loss and heat transference through that fabric is. We're looking for a lower U value as possible. So then the underfloor heating gets laid, it's in the screed, and then the floor covering goes on top. So the floor finishes are important. Carpets, you need to look at low TOG carpets if you use an underfloor heating. And you need to be mindful of engineered oak, wood laminate and tiles, that you don't go over certain temperatures that would either affect the wood or potentially scald into kids or people susceptible to temperatures on the underside of their feet in bathrooms, etc. But this is very, very good in terms of holding the heat because the heat is held in the screed and the insulation stops it going down to the slab and down into the ground. With regards to timber suspended floors, there's different methods. There's underfloor plates. There's also sections that sit on top of the floor. So again, you can have underfloor heating retrofitted, but it's more suited for new builds because of the height of the floor build-up, hence radiators, which is in this instance. So that's more of a retrofit scenario. And that's a general idea of what you would have for an underfloor heating layout. You'd have a manifold, which is supplied from the heat pump, and then it's zoned control. Again, the zone controlling helps you have more efficiency. So each of these zones is controlled. When it doesn't require heat, it basically shuts down the valves, and it's therefore more efficient. You're not blasting heat around the whole system like you might have with a radiator system. Even if you've got TRVs, it's still running at a fixed constant output. The important thing with radiators is that a lot of existing properties have got radiators based on older technology, i.e. gas boilers, LPG, or boilers, and they're based on 70-degree flow. Because heat pumps have a lower flow temperature, we need to be mindful that you've got a scenario where the radiators could potentially be undersized. So we're looking at what we call a delta T of 50 degrees. I won't go into it too much because it does get a bit complicated. And heat pumps are now looking at potentially a delta T of 30 rather than 50. This is why radiator sizing is so important for heat pump installation. And there's various charts provided by the manufacturers at 50 degree, which is the traditional, 30 degree for heat pumps. So if you just look at a standard radiator that's been sized for a traditional oil system or gas system, the output of this particular rate is 255 watts. If you're looking to use a heat pump, then that output at the given temperature would only be 133 watts. So therefore you would consider upping the radiator size specification to a bigger radiator with more surface area to accommodate the heat pump. This is something that's so important with retrofitting, and it should go hand in hand with the heat pump design. This is probably not relevant. I think that's something we can. The other option is that you can use fan-assisted fan convectors or fan-assisted radiators. Dimplex do them, Panasonic do them, Mitsubishi do them. It means you've got a smaller wall area to be taken up. The heat pump provides the hot water, and there's either one or two very small fans that pump it around the room. They can even be used in bedrooms on low speed, and it gets more heat into the room quickly, and it means that you've got less wall space. Downside is you do need an electrical socket adjacent so that you can actually run the fans. So these can run at a lower temperature, 40 degrees, less oversizing compared to the rads, and they do need that power supply. And the general term is smart rads. Most people use that term smart rads, not just Dimplex. Installation costs for underfloor heating, what we're looking at, you're talking about something like £10,500 for a new build, something like a 200-250 square metre property. You would have individual programmable room thermostats, which allow you to have that efficiency. And then onto the incentives. I've not done anything with the Green Home Grant because it's all retrofit, but generally speaking, that you could get £5,000 towards a heat pump or a solar thermal installation, which are deemed to be a primary measure. It's a little bit back to front on some of the things, in that ideally we would like to have seen double glazing retrofitting as a primary measure because it helps the heat pump performance. So if you're having a heat pump, you can get your windows done, but if you can't afford it, then really I think windows are more important than a heat pump for a lot of households. You can go up to £10,000 towards a heat pump system or the primary measure if you're on benefits such as universal credit or such like. So Green Homes Grant, it's just kicked off. It was as we're coming out of lockdown, there's been a few little issues and problems I think you're all aware of, which Nia has contacted your local MP, and it looks like it's helped to push that scheme being extended now from March 2021 to March 2022. The renewable heat incentive, now this is something that the Green Home Grant is in theory based on the requirements. The renewable heat incentive is the incentive that runs over 7 years for domestic and 20 years for non-domestic and commercial buildings. The important thing that also ties in with the Green Homes Grant, which has not been made clear, that the RHI payments and the Green Home Grant payments are based on the EPC Energy Performance Certificate for that property and how much heat energy is required to heat the property and provide hot water. Also tied in with that, if you remember the basic insulation requirements, it's mandatory for the RHI, and therefore it should be the same for the Green Homes Grant, that there is adequate loft insulation, i.e. 300mm, and that any cavity walls are filled. So again, if you look at the Green Homes Grant, you're in a situation whereby heat pumps and cavity walls are both primary measure, and therefore can you afford to have both of these and get the incentive? It's the way that it's been formatted that maybe could have been looked at a little bit better for homeowners. So we're in a position where the RHI is running parallel with the Green Homes Grant. This closes down for applications in March 2022. And it's domestic payments for a 7-year term. They're index linked, and once you're on board, it's set in stone. So they can't take that away, and it also, as I say, index linked, so it increases with inflation. The non-domestic offer a 20-year term. Again, it's index linked, and you get less in terms of the actual tariff payments, but it's for a longer term. This makes very good sense for commercial building if they're going to go for ground source heat pumps, which is metered, and they could get a big payment back that will cover the cost quite easily. The current tariffs at the moment for domestic are that you get 21.16 pence per kilowatt hour for renewable generated heat for a ground source heat pump, and 10.85 pence per kilowatt hour for an air source heat pump. And both these figures are capped at 20,000 kilowatt hours for an air source and 30,000 kilowatt hours for a ground source. So the good thing is that scheme is running parallel with the Green Homes Grant. However, you can't get the benefit of both grants. You would apply for your RHI, and then the Green Home Grant value of £5,000 is deducted from your total potential RHI payments. So therefore, over the period of each year, you receive less per year, and the Green Homes Grant basically is topping it up. You get the money up front, if that makes sense. So working them together strategically, it gives the homeowner the opportunity to get an element of money up front and still get a income stream to subsidise that installation over the next 7 years. And that, I think, concludes the presentation. Hopefully I've not gone too quick, but if there are any questions or you want to go back over anything, please do so.
Fantastic, thank you so much. What a wealth of information, and yeah, really, really clearly presented. I'm sure there are tons of questions.
Hope so.
Yeah, who wants to go first?
I think everybody's got their speaker off, so we might not be able to hear everybody.
How do we do this? So do people want to put it in the chat if you've got a question, or put your hands up on the video? I'm trying to see everyone. Okay. It's not everyone, is it? That's everyone. Yeah, not everyone's on video. But yeah, if people have got questions that they want to put.
Shall I give the screen back to you? Or no, you only get kid screen on me, don't you? No, that's fine. No. It's the same. I'm not sure how, because I can't see anyone at the moment, so you're in control of that, Nia.
Yeah, I've got a question just to start things off. So you mentioned that the for people with a gas boiler, you said you don't recommend people switching over because they're not going to save the amount of money.
Yeah. This is purely on a commercial side.
Yeah.
I'll explain that in a little bit more detail. We find there's two trains of thought. One is people who want to go for reduction in carbon footprint, sustainability going forward, looking for a greener future. That far outweighs the financial attitude of I've got to spend money on this heat pump. Other people look at it on the basis I want to do it, but I need to prove that I've got the right going forward the running costs, and I'm going to keep my running costs down. And they're not too worried about actually doing the installation and paying the capital cost, but they're looking at running costs going forward. And because the capital cost is quite high for a heat pump, especially if you didn't get the incentives, the running cost between gas and a heat pump is quite similar at the moment. We haven't got a crystal ball, so we don't know what's happening in the future. But my interpretation is that as gas becomes more scarce, there'll be a premium to pay for it. So the two trains of thought are, one is if you want to do it for the right reason, yeah, go for it. If you want to do it and you're looking for financial sense and financial common sense, then you need to consider it carefully.
Yeah, okay. So
it's important.
Save the world, then
yeah.
Do you break even, or does it?
It's difficult to say. It depends what your usage patterns are. We give a proposal that will give you a forecast.
Yeah.
To say this is what your running cost could be over 7 years.
Yeah.
And it can only be taken into account. We can't guarantee the weather, so we don't know how many bad winters. We don't know if there's going to be adequate heat for the heat pump. God forbid we come into a big freeze that goes on for months. You're going to find that an air source doesn't work as well, so your running costs go up. So as a generalisation, it's very nip and tuck at the moment with gas in terms of running costs. Yeah. So if you were to factor it in and say, well, I need to spend £13,000–14,000 on a heat pump, I do get money back, but can I afford to do it? That's the question.
Yeah.
But we have got clients who are doing it for the right reason, and they're saying, no, we want to go down that route for sustainability and looking for a greener future.
Cool, thank you. Yeah.
Does that make sense?
Yeah, no, that's really helpful. That's exactly, that's really helpful. Thank you. And Chris has just written, Christopher, I'm going to pick on you because you just written a question in the chat, which actually applies to me. So I'm sure it's not, I'm sure it applies to a few people. Yeah. If you want to ask your question.
Hiya. So I was just saying, I think a lot of our houses in Enfield are older properties, around sort of the 1900s and thereabouts, and not very well insulated. and the floors also might not be ideal. I think my understanding is that mine is timber on the ground floor with a little bit of concrete over it in the kitchen somewhere. And I
Yes.
wondered if you have any recommendations for properties like that. I've been told to go for big radiators rather than underfloor heating, but that seems a shame after I got quite excited about underfloor heating.
Right, there's so many different ways to look at this, Christopher. What you've got is a scenario where older housing stock is leaky in terms of insulation and heat losses. The biggest heat losses are through the roof and down through the floor. You've got options to look at with the Green Homes Grant, for example. You could potentially, if you can find someone who does it, because we've got a couple of clients who can't find people to do this work, you can actually insulate under the floorboards. There's different ways of doing it. Lift the floorboards, put insulation slabs underneath, quite a lot of work. Or there's other ones where they can actually blow things underneath, but you need to be mindful, obviously, of crossflow ventilation if it's required. Alternatively, you could look at underfloor heating and use an insulation board, but it increases the height of your floor. So it sounds as if that radiators, oversizing radiators might be the way to go, or fan-assisted radiators. But it is a big heat loss. And unless you're doing a major refurbishment, it's quite difficult to do a retrofit. I did a proposal and heat loss calculations for a potential client over at Winchmore Hill a few weeks back. And what I do is on certain properties, I say that we've got to do room heat loss calculation, which is mandatory under the NCS requirements that we sign up to. And what I do, I offer certain clients the opportunity for me to do the heat loss calcs beforehand for a nominal fee. In this instance, we did the heat loss calcs and went through it with the client, and he said, no, I'm glad you did this. It shows that I would have to have big radiators, and I don't want to do that. And also, I need a larger heat pump than a competitor had told him. So what he did, he said, well, I'm going to stick with a gas boiler and put a gas boiler in. It's going to be a highly efficient 96-97% efficient gas boiler. He wanted to maintain room wall space, therefore to put the radiators in, as you quite rightly said, was something he wasn't keen on. So therefore it probably doesn't work as well. If you did put radiators in and didn't beef up the insulation, would a heat pump be suitable in terms of efficiency? I would rather say in that instance maybe that you should look at the insulation levels, and it will still benefit with your gas boiler, but you're not wasting time and money on a heat pump. Does that make sense?
Yeah, thank you. That does make sense.
Yeah, it's just a case of being honest and saying that in some instances it won't work.
So when you say it won't work, is it just that you may not get your money back, or is it just like not working?
No, sometimes it will not work because it's fighting all the time to actually keep up with the heat losses. So this is why we say sometimes, look, consider increasing your insulation levels, upgrade your glazing to double glazing, and then maybe consider a heat pump later. But it's all money. You're spending money on all this, and you know, some people have got the salesman attitude where they're trying to sell boxes and they don't care on the periphery. Whereas we would rather say, well, look, even if you can't really say a heat pump's going to work correctly, it will work, but it's not going to work efficiently. And you could be spending hand over fist on running costs to maintain the heat level, the comfort levels in that property. But Christopher, you're right. You need to upgrade your radiators if necessary to suit the heat pump operation. Or you increase your insulation levels, the radiators might be fine and the heat pump works okay.
Thanks.
Thank you. Any other questions? Everyone understood that perfectly then. You obviously gave a very, very clear explanation. Fantastic. So I'm sure, so Jeff's email address is publicly available. That's how I got it. So if you don't mind me saying, I'm sure if people have questions that they want to follow up with.
Yeah, sure. No problem at all. No problem. It's best to do it by email. We're having problems with the phones, both the landline and the mobiles at the moment. So email would be good. If you just say that you've attended the presentation, and I'll do my best to get back to you with further information or answers.
Cool, thank you. Do you mind me passing that on to people?
No problem at all.
Cool, thank you.
No problem. But if you've been with us, we're going through a very busy period at the moment because we've come out of lockdown. It's just gone mad with people re-energising old projects. And a lot of ours are new builds or major refurbishments. rather than retrofit. As I say, it's a case of the government have brought in this wonderful Green Homes grant without looking at what's happening in the periphery. So yeah, we will get back to you, but it's just a case of we are triple busy, which is good, and it just shows there's a lot of interest in renewables.
Is the solar PV better if you've got a leaky, drafty house?
No, it doesn't do anything in respect of obviously affecting your heat losses. What it could do is...
But does it just at least work and give you some heat? But inefficient? Yeah,
basically, you've got two things with PV that you can look at. One is that you still get sunlight in winter. There's less sunlight hours. But PV likes cooler weather better than the hot temperatures we get in summer. So you're going to get more harvesting at a given time with PV during the winter with that nice, crisp, cold morning with loads of sunlight, because it likes that coolness. So yeah, and then your heating's running, and that will be powering your heat pump. But importantly, during summer, you've got two options. It could be running the heat pump, and therefore you would only want to run the heat pump in hot water mode. So you would have it there as a backup, so to speak. But your PV, you could actually use a power diverter. Did the guy who did your PV seminar tell you about the power diverters for immersion heaters?
It was solar panels, but not PV. It was just for electricity. So
solar. Yeah, was it solar thermal or solar PV?
Yeah, no, solar electric.
Yeah, okay. No, so you got the PV can also control the immersion heater to put the self-generating energy into your cylinder to heat your hot water. Therefore, the heat pump wouldn't need to run. But the solar thermal, again in summer, you would be using all that heat energy, and you would then put it into your coil. And again, the heat pump wouldn't need to run. It would only be there to back it up. So it is a good technology, and it's probably the most raw energy you can get from a renewable technology. It's obviously not totally renewable because you've got an element of electricity going in. So as long as your supply is renewable, you can actually say that you've got all that raw energy that would heat your cylinder up to maybe 60, 70 degrees quite easily during the summer. And you could say between 75, maybe 90% of your energy bill through your solar thermal. And you could also save it through your solar PV.
Cool. Yeah, that sounds good then. Fantastic. Thank you. Well, Chris has got another question. Do you want to ask your second question, Chris?
Yep, go for it.
It's not actually from me. It's from I let some of my friends know that that the talk was being given, and they were just wondering what is the typical yield / time to pay it back
on a heat pump?
Yeah.
If you're looking at the government subsidies, you should get your payback within 7 years. It all depends on what fuel that you are replacing or comparing to. If you're looking at pure electricity, it's going to pay itself back potentially, depending on your usage, well within a 7-year period. If you're looking at oil or LPG and you've got the incentive on board, it should pay back within that period. If not, maybe just a short while more. So let's say with an air source heat pump of a certain size, you've got your subsidies running for 7 years with the RHI, you should pay back 8 or 9 years. But then the life of the heat pump compared to a gas boiler is 15 to 20 years. So you're going to get potentially maybe something like 12 years of free, not free, but free usage rather than worrying about the payback of the capital cost. You're still paying your bills, but you should be able to get that back within an 8-year period on a certain size system. Ground source is slightly different, and it depends what you're comparing to. So it's quite difficult. Solar PV is easier to calculate, and we would say that on an average 4-kilowatt PV system, payback 16, 17 years, depending on what system and what kit you've got, maybe a little bit less. But heat pumps, I think you're going to find it's a quicker payback on air source, not so much on ground source.
Thank you.
Thank you. Any more? What should we let? Should we all let Jeff have his dinner? So yeah, thank you again for everyone for coming.
You're welcome.
Really fantastic. And yeah, thank you, Jeff, for a really, really great talk. And yeah, I've certainly learnt lots and lots of thoughts. So yeah, I hope to catch up with all of you soon.